There is something extraordinary just above our heads, something we almost never notice. It has no sharp boundary, no color of its own, and yet it shapes every moment of our existence. Earth's atmosphere is more than just the air we breathe. It is a dynamic, invisible shield that protects us from the vacuum of space, the fury of solar radiation, and the chill of absolute cold. Without it, life as we know it would not just be impossible, it would never have begun. And yet, this vast, multi-layered envelope is still full of mysteries waiting to be understood. Today, we embark on a journey to explore this unseen world. From the troposphere, where clouds gather and storms are born, to the outer reaches of the exosphere, where particles drift into space, each layer of our atmosphere plays a crucial role. Along the way, we will uncover breathtaking optical illusions, invisible energy fields, and cloud formations so strange they were not officially recognized until the 21st century. Let us take a deep breath and step into the great unseen world that makes life on Earth possible. When we look up at the sky, we often forget that we are peering into one of the most complex and essential systems on our planet. The atmosphere is not simply a blanket of air. It is a finely tuned, multi-layered structure that makes life on Earth possible. It gives us the oxygen we breathe, shields us from deadly solar and cosmic radiation, and moderates the planet's temperature so that water can remain liquid and ecosystems can thrive. Without this invisible envelope, Earth would be a barren, frozen rock, scorched by sunlight during the day and plunged into darkness and deadly cold at night. The atmosphere is divided into several distinct layers, each with its own characteristics and functions. These are the Troposphere, Stratosphere, Mesosphere, Thermosphere, and Exosphere. While these names might sound technical, they represent critical boundaries where temperature, density, and composition shift dramatically. Each layer plays a vital role in protecting our planet and shaping the conditions we experience on the surface. From clouds and weather in the lower atmosphere to auroras and satellites in the upper layers, the atmosphere is not static. It is constantly in motion, responding to the sun, the oceans, and even human activity. This atmospheric structure is not fixed in place. Its height, composition, and behavior change depending on time of day, latitude, season, and solar activity. For example, the troposphere, the lowest layer where we live, can range from about 7 kilometers above the poles to nearly 20 kilometers at the equator. Above that lies the stratosphere, where ozone absorbs harmful ultraviolet light. Farther still is the mesosphere, where meteors burn up, and the thermosphere, where temperatures can soar to thousands of degrees due to solar radiation. Finally, the exosphere marks the slow transition from Earth's air to the vacuum of space. In this video, we will travel through each of these layers, exploring not only their physical structure, but also the hidden forces at work within them. We will witness rare cloud formations, stunning optical effects, and powerful energy fields that shape the world we know. Some of these phenomena are well understood. Others remain mysterious, only recently confirmed by satellite and rocket missions. As we ascend from ground level to the edge of space, we will discover that the atmosphere is not just a protective shell. It is a vast and living system, as dynamic and beautiful as the life it supports. The troposphere is the lowest and most familiar layer of Earth's atmosphere. It begins at the surface and extends upwards to an average height of 17 kilometers in mid-latitude regions, around 20 kilometers at the equator, and only about 7 kilometers near the poles during winter. Though it is the thinnest of the atmospheric layers, it contains approximately 75% of the total mass of the atmosphere and nearly all of the water vapor and weather systems that impact daily life. This is the realm of clouds, rain, wind, storms, and snow. In many ways, it is the breathing, living skin of the planet. What makes the troposphere so dynamic is its relationship with temperature and altitude. In this layer, the higher you go, the colder it becomes. This gradient, known as the lapse rate, typically decreases by about 6.5 degrees Celsius for every kilometer you ascend. It is why snow can linger on mountaintops even in summer, while the valleys below bask in warm sunshine. The reason lies in the physics of heat transfer. Solar energy passes through the atmosphere mostly unimpeded and is absorbed by the Earth's surface. That surface then re-radiates the heat upward through conduction and convection, warming the lower atmosphere from the ground up. When the ground absorbs sunlight, it heats the air immediately above it. Warmer air, being less dense, expands and rises, while cooler, denser air sinks to take its place. This circulation pattern is called convection. It is a powerful engine for weather and wind, transporting heat and moisture throughout the lower atmosphere. Where warm, moist air rises rapidly, towering storm clouds can form, and with them, lightning, thunder, and heavy rainfall. The troposphere is in constant motion due to these convection currents, stirred further by Earth's rotation and the contrast between equatorial and polar temperatures. This difference in solar heating gives rise to large atmospheric circulation cells, such as the Hadley cells near the equator, Ferrel cells in the mid-latitudes, and polar cells near the poles. Within these structures, rising and sinking air masses regulate global climate and wind patterns. In tropical regions, intense solar energy causes hot air to rise high into the troposphere. As it rises, it cools and spreads toward the poles before sinking back down around 30 degrees latitude. These zones of descending dry air are the reason many of the world's great deserts, like the Sahara and the Australian outback, exist in these latitudes. The troposphere's composition is relatively uniform around the globe, a mixture of about 78% nitrogen, 20% oxygen, and trace amounts of carbon dioxide, argon, and other gases. However, one component varies dramatically: water vapor. This invisible gas, produced by evaporation and transpiration, is a key driver of weather. As moist air rises and cools, the water vapor condenses around tiny particles like dust or salt, forming droplets. These droplets group into clouds, and when they become heavy enough, they fall as precipitation. Even the smallest cloud can contain millions of droplets in a single cubic meter of air. At the top of the troposphere lies the tropopause, a boundary layer where the lapse rate, the rate at which temperature decreases with height, suddenly stops. Above this point, temperature begins to increase again, signaling the start of the stratosphere. The tropopause acts as a lid, preventing most vertical air movement from extending farther upward. That is why most weather phenomena are confined to the troposphere. Commercial airliners often fly just above this layer to avoid turbulence and storms. Though it may seem ordinary to us, the troposphere is an extraordinary space, both delicate and resilient, chaotic yet ordered, and profoundly essential to all life below. Rising above the troposphere is a calmer, more stable layer known as the stratosphere. It stretches from approximately 20 kilometers above the Earth's surface at the equator to about 50 kilometers in altitude. Unlike the turbulent and churning nature of the troposphere, the stratosphere is stratified. Its name comes from the Latin stratum, meaning layer. Here, air moves mostly in horizontal flows, and vertical mixing is minimal. This layered stability gives the stratosphere its defining trait, a reversal in the temperature gradient. As we ascend through the stratosphere, temperatures actually increase with height, a phenomenon that sets it apart from the layers above and below. This warming trend is caused by one of the most important components of our atmosphere, the ozone layer. Located within the stratosphere, roughly between 15 and 35 kilometers above the surface, the ozone layer acts as a protective shield that absorbs a significant portion of the sun's harmful ultraviolet radiation. Ozone is a molecule made of 3 oxygen atoms, written chemically as O3. It forms when ultraviolet light splits apart oxygen molecules, O2, allowing single oxygen atoms to recombine with others. This process also releases heat, which warms the surrounding air and causes the temperature rise with altitude. Though ozone makes up only a tiny fraction of the atmosphere, around 10 parts per million in its highest concentrations, it plays a critical role in shielding all life on Earth. Without this invisible barrier, ultraviolet radiation would reach the surface in far greater intensity, damaging DNA in plants, animals, and humans alike. Skin cancers, cataracts, and widespread ecological damage would be far more common in a world without ozone. The discovery of the ozone layer's depletion in the late 20th century led to urgent international action, including the Montreal Protocol, a landmark agreement that has helped reduce ozone-destroying chemicals in the atmosphere. Because the stratosphere is drier and more stable than the layers below, it is rarely home to clouds or storms. However, there are rare exceptions. In polar regions, especially during winter, strange and beautiful formations known as polar stratospheric clouds can appear. These clouds do not consist of water like typical clouds, but are made from compounds such as nitric acid and frozen aerosols. They are often responsible for reactions that damage ozone, particularly when sunlight returns in spring and triggers photochemical processes on their icy surfaces. Despite their role in ozone depletion, these clouds produce brilliant iridescent displays when illuminated from below by the rising or setting sun. The stratosphere's calm, dry conditions also make it a preferred environment for high-altitude aircraft. Most commercial airliners cruise at the lower edge of the stratosphere, just above the troposphere, to avoid turbulence, storms, and clouds. In this region, the air is thin but smooth, allowing for fuel-efficient travel and a more comfortable ride. In 2012, the world watched as Felix Baumgartner ascended to nearly 39 kilometers above Earth, still within the stratosphere, before making a supersonic free fall back to the surface. His historic jump highlighted just how expansive this layer truly is, stretching over twice as far as Mount Everest is tall. At the top of the stratosphere lies the stratopause, the boundary that marks the transition to the mesosphere above. Here, the temperature peaks once more before beginning to fall again in the higher layers. Though we seldom think of it, the stratosphere is a vital guardian in the sky, calm, layered, and quietly powerful. It absorbs deadly radiation, provides a stable platform for flight, and shapes the conditions of our world in ways we rarely see but constantly benefit from. As we continue our journey upward, we leave behind the warmth of the ozone and enter a colder, thinner, and more mysterious realm, the Mesosphere. Temperatures in the mesosphere drop drastically with altitude, reaching some of the coldest known in the entire atmosphere. Near its upper boundary, temperatures can plunge below -100 degrees Celsius. This intense chill is not just a number, it has tangible consequences. It is in this frigid environment that meteors, speeding into Earth's atmosphere from space, begin to burn up. The friction generated as they collide with molecules in the mesosphere causes them to flare and disintegrate in spectacular streaks of light across the night sky. These meteor trails, though brief, are one of the few visible signs of activity in this layer. Despite its dryness and thinness, the Mesosphere is home to one of the most breathtaking and enigmatic atmospheric displays ever recorded: Noctilucent clouds. These clouds, whose name means night shining, form at extremely high altitudes between 76 and 85 kilometers above the surface. They are composed of tiny ice crystals, less than 100 nanometers in diameter, and only become visible during twilight hours, when the sun has dipped below the horizon but still illuminates the upper atmosphere. The result is a shimmering, ghostly glow, pale blue or silver, set against the deepening dusk. Noctilucent clouds are rare and require an unusual set of conditions to form. The mesosphere must be cold enough, colder than -120 degrees Celsius, and there must be microscopic particles for water vapor to condense onto. The origins of these particles remain uncertain. Some may come from space, delivered by micrometeorites that disintegrate in the mesosphere and leave behind dust. Others may arise from volcanic eruptions or even rocket exhaust. When water vapor rises high enough and temperatures plummet low enough, the vapor condenses around these particles and creates the fine ice crystals that make up the clouds. Unlike typical clouds in the troposphere, which form through convection and are influenced by local weather patterns, Noctilucent clouds are shaped by subtle changes in atmospheric circulation. They appear most frequently during summer months and at high latitudes, between 50 and 70 degrees north or south of the equator, where the mesosphere is paradoxically colder than during winter. This seasonal cooling is caused by upwelling air currents that rise from the lower atmosphere, expand, and cool as they ascend. The result is a cold, still canvas upon which the upper atmosphere paints these luminous, delicate patterns. For scientists, Noctilucent clouds are not just visually captivating, they are also important indicators of change. Their frequency and brightness have increased in recent decades, prompting researchers to investigate links with climate change and human activity. As greenhouse gases warm the lower atmosphere, they may cause cooling in the mesosphere, creating more favorable conditions for Noctilucent clouds to form. In this way, these ethereal formations are more than just a spectacle. They may also serve as a silent message from the upper sky, reminding us that even the most distant layers of the atmosphere are intimately connected to life below. Above the mesosphere, where temperatures reach their coldest, lies a layer that seems almost paradoxical: the thermosphere. Its name comes from the Greek word for heat, and for good reason. In this region, which begins around 85 kilometers above Earth and extends upward to nearly 600 kilometers, temperatures can soar to astonishing heights. During periods of strong solar activity, the few particles found here can reach temperatures above 2,000 degrees Celsius. But this heat is deceptive. Because the air is so thin, there are too few particles to transfer warmth to your skin. If you could stand there, it would still feel freezing cold. The thermosphere is vast and diffuse, containing less than a fraction of a percent of Earth's atmospheric mass. Yet, it is home to some of the most iconic phenomena ever witnessed in the sky. It is in this layer that the Aurora Borealis and Aurora Australis, commonly known as the Northern and Southern Lights, come to life. These breathtaking displays of dancing color occur when charged particles from the sun are funneled by Earth's magnetic field into the upper atmosphere, where they collide with atoms and molecules of oxygen and nitrogen. These collisions release energy in the form of light, producing glowing ribbons of green, red, violet, and blue. Though auroras are most commonly seen in polar regions, they can occasionally appear farther south during periods of intense solar storms. The specific colors of an aurora depend on which atmospheric gases are involved and how much energy is transferred during the collision. Green light, for example, is produced when energetic particles strike oxygen atoms about 100 kilometers above the ground. Red auroras occur at even higher altitudes, while purples and blues are associated with nitrogen. These luminous curtains of light ripple and shimmer silently, turning the thermosphere into a natural theater of electromagnetic energy. The thermosphere also plays a critical role in modern human technology. It is within this layer that many satellites orbit the planet, including the International Space Station, which circles Earth at an altitude of roughly 400 kilometers. These spacecraft must contend with atmospheric drag from the residual gases still present in the thermosphere. Though sparse, these particles are enough to gradually reduce orbital speeds, requiring regular course corrections. The thermosphere also absorbs much of the sun's high-energy ultraviolet and X-ray radiation, protecting the layers below and influencing long-term patterns in atmospheric circulation and climate. At the very top of the thermosphere lies a shifting boundary called the thermopause, which separates this layer from the exosphere beyond. The height of the thermopause varies depending on solar activity, stretching higher when the sun is active and contracting when it is calm. Though we seldom feel its presence, the thermosphere is a region of profound importance, a zone where light meets particle, where the sun touches Earth, and where beauty and physics converge. It reminds us that even in the near silence of space, the atmosphere continues to speak, through color, motion, and the glowing breath of the aurora. At the outermost edge of Earth's atmosphere lies a layer so faint, so ethereal, that it blurs the line between planet and space. This is the exosphere, the final frontier of the atmosphere, beginning around 600 kilometers above Earth and stretching tens of thousands of kilometers into space. Unlike the layers below, the exosphere does not have a well-defined upper boundary. It gradually fades into the vacuum of interplanetary space, where solar wind and cosmic radiation roam freely. Here, atoms are so widely spaced that they rarely collide, moving along ballistic trajectories, governed more by gravity and radiation pressure than by air dynamics. The exosphere is composed primarily of extremely light gases, such as hydrogen and helium. These particles drift slowly, sometimes for hours or even days, before interacting with another atom. Because of this lack of collision and coherence, the exosphere behaves less like a gas and more like a transitional zone, a twilight between Earth and the stars. While it may seem empty, it still remains gravitationally bound to the planet. The outermost particles, however, can eventually escape into space, contributing to the slow, steady loss of Earth's atmosphere over geological timescales. Despite its sparse nature, the exosphere plays a vital role in the interaction between Earth and the wider cosmos. It serves as the outer boundary of our planet's protective shield, absorbing and deflecting energetic particles from the solar wind. Some of these particles are captured by Earth's magnetic field and directed into lower layers, creating auroras. Others are deflected entirely. The exosphere is also where many scientific satellites operate, as its low particle density reduces drag. Communications, navigation, weather tracking, and Earth observation all depend on instruments floating within this tenuous veil. It is here, in the exosphere, that Earth's atmosphere gives way to the realm of deep space. The sun's radiation becomes dominant, pushing against the outermost gas particles until they can no longer resist. At distances beyond 10,000 kilometers, solar radiation pressure often overcomes Earth's gravitational pull, allowing hydrogen atoms to escape into the solar system. This subtle bleeding of atmosphere into space is an ongoing process, invisible yet constant. While it may sound alarming, it occurs slowly enough that Earth's habitability remains secure for billions of years. In many ways, the exosphere is not so much a place as it is a transition, a vast, whisper-thin gateway between the known and the unknown. It reminds us how fragile our environment truly is, and how delicately Earth is suspended within the forces of the solar system. From the troposphere's storms to the exosphere's silence, our atmosphere is a continuum of motion, light, and protection. And just beyond it lies the cosmic sea, where Earth sails quietly, wrapped in its invisible cloak of air. As we prepare to leave the atmosphere and enter the vastness of space, we begin to see Earth for what it truly is: a blue island, alone, but not unprotected. High above the poles, far from the equator's warmth, a massive system of swirling air dominates the upper atmosphere. It is called the polar vortex, and it exists at both the north and south poles. Unlike a tornado or a hurricane, the polar vortex is not a single storm, but a vast region of low-pressure, frigid air trapped high above the polar regions. This air spins counterclockwise in the northern hemisphere and clockwise in the southern hemisphere, shaped and maintained by Earth's rotation and temperature gradients. It stretches from the troposphere through the stratosphere, and sometimes even into the mesosphere, spanning thousands of kilometers. The polar vortex is held in place by a powerful band of wind known as the polar night jet. This high-altitude jet stream circles the polar regions at the boundary between the frigid polar air and the warmer air farther south. It acts like an invisible wall, containing the icy core of the vortex and preventing it from spilling into lower latitudes. The strength of this jet stream depends on the temperature difference between the polar region and the mid-latitudes. During winter, when the pole is in complete darkness and the temperature gradient is at its steepest, the polar night jet becomes especially strong and tightly wound. But the balance does not always hold. Sudden disruptions, such as warming events in the stratosphere or planetary wave interference, can weaken or even shatter the polar night jet. When this happens, the tightly coiled vortex begins to unravel. Arctic air, once locked in place, spills outward and drifts southward, carried on distorted jet stream pathways. This breakdown can lead to dramatic cold snaps in Europe, North America, and parts of Asia. In recent years, such polar vortex disruptions have been linked to severe winter storms, transportation shutdowns, energy crises, and widespread societal impacts. A breach in this wall of wind can change entire weather patterns for weeks. Scientists have long studied the polar vortex, not only for its immediate weather effects, but also for what it reveals about the changing climate. Some research suggests that a warming Arctic may destabilize the vortex more frequently, weakening the polar night jet and increasing the chances of cold outbreaks in temperate regions. This paradox, where global warming contributes to regional cooling events, is a reminder of how deeply interconnected the atmospheric system is. Shifts in ocean temperatures, melting sea ice, and changes in solar radiation can all affect the strength and structure of this upper-level circulation. To the casual observer, the polar vortex might seem like a distant curiosity, an abstract mechanism far above daily life. But in truth, it is a hidden force that governs the rhythms of winter and protects climate zones from chaos. The polar night jet, strong and silent, is a kind of atmospheric guardian. When it holds, the world remains ordered. When it breaks, the cold descends with astonishing speed. Understanding this system is not only a scientific challenge, it is a necessity for forecasting the future of life on a warming planet. In the battle between heat and cold, light and darkness, the polar vortex is one of Earth's most formidable players. When the polar vortex loses stability, the consequences are rarely confined to the skies above. On the surface, its disruption can unleash devastating cold across continents. Sudden plunges in temperature, unrelenting snowstorms, and prolonged freezes can cripple infrastructure and overwhelm cities. One of the most striking examples occurred during the winter of 2010 in the United Kingdom. Known as the Big Freeze, this event brought record-setting cold to large swaths of the country. Scotland saw temperatures fall below -20 degrees Celsius, while transportation networks ground to a halt and power outages left thousands in the dark. In North America, the effects have been even more dramatic. In early 2019, a fractured polar vortex descended upon the Midwest, turning major cities into frozen landscapes. Chicago, often referred to as the Windy City, experienced wind chills colder than parts of Antarctica. Flights were canceled, schools closed, and emergency shelters overflowed as people tried to escape the dangerous cold. Some regions recorded wind chill values near -50 degrees Celsius. In the aftermath, hospitals reported hundreds of frostbite cases, and dozens of deaths were attributed directly to the extreme weather. What makes these events especially dangerous is not only their severity, but also their unpredictability. The breakdown of the polar night jet can unfold in a matter of days, giving meteorologists limited time to forecast its trajectory and warn the public. Sudden stratospheric warmings, rapid increases in stratospheric temperatures that often precede a vortex collapse, can destabilize jet streams thousands of kilometers away. Once the vortex is broken, the cold air does not merely seep south, it surges. Areas unaccustomed to extreme cold may find themselves woefully unprepared, with aging infrastructure unable to cope with prolonged freezing conditions. The socioeconomic impacts of such events are profound. Power grids strain under increased demand, water lines burst beneath frozen soil, and roads become impassable under sheets of ice. Agriculture suffers as crops freeze and livestock are lost to exposure. Commerce slows, healthcare systems are pushed to the brink, and vulnerable populations face life-threatening conditions. For lower-income communities, where heating systems may be unreliable or unaffordable, the consequences can be dire. In the United States alone, damages from polar vortex events over the past decade have totaled in the billions of dollars, highlighting how atmospheric breakdowns translate directly into human hardship. As the planet continues to warm, the polar vortex may become less stable, not more. This counterintuitive reality raises urgent questions about the future of winter in temperate regions. Will these devastating cold snaps become more frequent? Are current infrastructure systems prepared to withstand more of them? And what policies must be enacted to protect people in the path of these atmospheric disruptions? The polar vortex is not just a scientific curiosity. It is a force with the power to reshape human experience. When it falters, the sky darkens, the air turns sharp, and entire societies are forced to adapt. In the dance between order and chaos, the vortex is both conductor and warning sign. When we think of Earth's protective systems, we often picture its magnetic field or gravitational pull, two powerful forces that shield and shape life on our planet. But recent discoveries have revealed a third, lesser-known energy field that quietly governs the upper atmosphere and helps regulate Earth's long-term habitability. It is called the Ambipolar electric field, and though invisible, it plays a critical role in how particles escape into space. For decades, this field was only a theoretical construct. Scientists believed it was too weak to detect, its presence hinted at only through indirect clues in the motion of charged particles high above the surface. That changed in the year 2022, when a team of NASA scientists launched a suborbital mission from Svalbard, Norway, one of the northernmost rocket ranges on Earth. The mission, called Endurance, carried a specially designed instrument called a photoelectron spectrometer into the upper atmosphere. Its task was to measure the speed of escaping electrons and detect subtle changes caused by the presence of an electric field. At an altitude of over 700 kilometers, the instrument recorded a voltage difference of just over 0.5 volts, barely more than the power of a watch battery. Yet this faint force was enough to confirm the existence of Earth's ambipolar field for the very first time. So, what exactly is the ambipolar electric field, and why does it matter? High in the ionosphere, where sunlight ionizes atoms and creates a plasma of free electrons and positive ions, an electric imbalance forms. The lighter electrons tend to escape upward more quickly than the heavier ions, but their opposite charges create a tug of war. This competition generates an electric field, one that exerts upward pressure on the ions and helps accelerate them into space. This is the mechanism behind the polar wind, a slow but steady outflow of charged particles from the poles into the vacuum beyond. It is a process that has been occurring for billions of years, shaping the evolution of Earth's atmosphere. Though this polar wind may seem insignificant on a daily basis, it has cosmic consequences. Earth loses about 3 kilograms of hydrogen to space every second, along with smaller amounts of helium and oxygen. Over geological time, this slow escape has contributed to the thinning of the upper atmosphere and the long-term evolution of planetary conditions. What is even more remarkable is that Earth's ambipolar field is unusually weak, far weaker than that of Venus, whose stronger electric field may have played a role in stripping away its water and making the planet dry and inhospitable. In this light, Earth's modest ambipolar field may be one of the reasons our world has retained its oceans and atmosphere. The discovery of this third global energy field changes how we understand Earth as a system. It adds a new layer of complexity to atmospheric science and provides a critical piece of the puzzle in understanding why Earth, and not its planetary neighbors, remains a cradle for life. As future missions continue to explore the ionosphere and beyond, scientists hope to map the full structure and behavior of the ambipolar field, and perhaps use that knowledge to study exoplanets in distant solar systems. From the deepest clouds to the outer edge of space, we are beginning to realize that Earth's protection comes not from one shield, but from a symphony of forces working together in balance and silence. High above the surface of Earth, in a realm colder than any place you have ever stood, an ethereal display sometimes graces the night sky. These are Noctilucent clouds, delicate, shimmering veils of ice that drift silently at the edge of space. Their name means night shining, and they are unlike any other clouds you have ever seen. Suspended between 76 and 85 kilometers above the ground, they reside within the upper Mesosphere, making them the highest known cloud formations in Earth's atmosphere. Their glow is not their own, but a reflection of sunlight that brushes the upper edge of the planet even after the surface has fallen into darkness. Noctilucent clouds require extraordinarily rare conditions to form. Temperatures must drop far below -100 degrees Celsius, and there must be water vapor and microscopic particles on which the vapor can condense. The origin of these particles is a subject of ongoing research. Some scientists believe they come from micrometeoroids, tiny fragments of space dust that burn up in the upper atmosphere. Others suggest volcanic eruptions, rocket exhaust, or even particles from climate processes far below may be responsible. Once the ice crystals form, they drift slowly on high-altitude winds, catching twilight light and glowing with a soft, silver-blue luminescence. These clouds are most visible during the summer months and at high latitudes, between 50 and 70 degrees north or south. It is a paradox of the upper atmosphere. The coldest temperatures in the mesosphere occur during the warmest season on the ground. This happens because warm air rises from the troposphere, expands as it ascends, and cools adiabatically, producing a chill that allows Noctilucent clouds to form. Observers in places such as Alaska, Scotland, and northern Canada often report sightings during late June and early July, when the twilight conditions are ideal and the mesosphere reaches its coldest point. In recent decades, scientists have noticed that Noctilucent clouds are appearing more frequently and at lower latitudes than ever before. Some believe this may be a sign of broader changes in our planet's climate system. As greenhouse gases warm the lower atmosphere, they may also cool the upper layers, making the mesosphere even more favorable for the formation of these clouds. At the same time, increased human activity may be injecting more water vapor and particulates into the upper atmosphere. In this way, Noctilucent clouds have become a kind of atmospheric messenger, a visible signal that even the highest reaches of the sky are not immune to human influence. To the casual viewer, Noctilucent clouds may appear as a fleeting beauty, an unusual glow before dawn or after sunset. But to scientists and sky watchers, they represent something far deeper, a connection between the Earth's surface and the edge of space, between human action and atmospheric response. Their haunting beauty reminds us of the fragility of the planet's climate and the silent processes unfolding high above us. They are clouds of cold, born in stillness, glowing with light that no longer touches the ground. And in their quiet shimmer, they whisper that the sky is watching and that it remembers everything. Imagine standing beneath a sky that looks like the surface of a turbulent sea, dark, roiling, and full of menace. Waves seem to hang upside down, sculpted in cloud, like a storm frozen mid-motion. These are Asperitas Clouds, one of the most unusual and dramatic formations ever recorded in Earth's atmosphere. Their name comes from the Latin word for roughness, and it is fitting. With their undulating, jagged appearance, Asperitas clouds are unlike any other cloud type. They evoke awe, confusion, and even a sense of unease. Until recently, they were not even officially recognized in the International Cloud Atlas. It was only in the year 2017 that the World Meteorological Organization formally added Asperitas clouds to its classification system, the first new cloud type to be included in nearly 70 years. The push came not from professional scientists, but from citizen observers. Amateur cloud watchers began sharing photographs online of strange formations they had never seen in textbooks. Through the work of the Cloud Appreciation Society, a collection of stunning images and field reports was compiled, eventually convincing meteorologists that they were witnessing something genuinely new. In many ways, Asperitas clouds were discovered by the public, crowdsourced from the sky. Asperitas clouds typically form beneath stratiform cloud layers and are believed to be shaped by complex wave motions within the atmosphere. While other wavy cloud types, like undulatus, have smooth and rhythmic patterns, Asperitas clouds are more chaotic, marked by abrupt shifts, sharp valleys, and jagged peaks. The most common theory is that they are produced by gravity waves, oscillations that occur when a stable layer of air is disturbed by a force such as a mountain range, a thunderstorm, or a shift in temperature. When these waves interact with moisture-laden cloud decks, they can sculpt the dramatic underbellies seen in Asperitas formations. Though visually menacing, Asperitas clouds do not necessarily bring severe weather. They often appear after a thunderstorm has passed or when atmospheric conditions are transitioning. Their drama is more visual than destructive. Yet, their very existence challenges how we understand atmospheric motion. The turbulence that creates them is typically hidden from view, occurring within layers of wind shear and shifting pressure. With Asperitas clouds, those internal battles are revealed, drawn out across the sky like brushstrokes in a painting made by the wind. In that sense, they offer a rare glimpse into the fluid, living nature of the atmosphere. To see Asperitas clouds is to feel the pulse of the sky itself, its agitation, its shifting moods, its capacity for both structure and chaos. They are fleeting, and no two displays are ever the same. Like other rare phenomena in our skies, they remind us that the atmosphere is not a static shell, but a vast, restless ocean of air, shaped by forces both visible and invisible. Whether captured by a camera or simply remembered in awe, Asperitas clouds leave an impression that lingers. They are not just clouds, they are expressions of energy, movement, and the hidden rhythms of our planet's breath. Sometimes, if you gaze toward the sun on a crisp, cold morning, or toward the moon on a clear winter night, you might notice a faint ring in the sky, delicate yet striking. It may look like a rainbow, but it is not born from rain. Instead, it is formed from ice. These are ice halos, luminous circles and arcs that appear when sunlight or moonlight is refracted through millions of tiny hexagonal ice crystals suspended high in the atmosphere. Unlike rainbows, which form in the troposphere, ice halos originate far above, within cirrus or cirrostratus clouds, drifting between 5 and 10 kilometers above the Earth. The most common of these phenomena is the 22-degree halo, named for its radius, an optical ring that appears roughly 22 degrees away from the sun or moon. These halos occur when light enters one face of a hexagonal ice crystal and exits through another, bending the beam at a fixed angle. This refraction causes the light to spread into its component colors, often leaving a soft reddish inner edge and a bluish outer rim. Sometimes, additional arcs or bright spots form, known as sundogs or parhelia, positioned like twin mock suns to the left and right of the real one, shimmering in the cold. The diversity of ice halos is astonishing. There are circumzenithal arcs, which appear like upside-down rainbows directly overhead, and tangent arcs, which skim the edges of the halo like ethereal wings. There are light pillars, which rise vertically from bright sources, and rare events like the parhelic circle or the elusive Bottlinger's rings. These intricate forms are determined by the shape, orientation, and motion of the ice crystals. Plate-shaped crystals falling horizontally produce one effect. Column-shaped crystals tumbling through the sky yield another. The atmosphere becomes a canvas, and sunlight, or moonlight, the artist's brush, scattering light into geometry. Though many ice halos are subtle and easy to miss, others are vivid and unforgettable. In the polar regions, especially during the long winter nights, halos illuminated by a full moon can create an otherworldly display. Silver rings, bright spears of light, and shimmering arcs that stretch across the entire sky. In rare cases, artificial lights shining upward through ice crystals near the ground can create dazzling vertical columns, making cities look as though they are illuminated by a frozen aurora. Such displays often feel too perfect to be real, evoking a sense of wonder, even disbelief. Ice halos remind us that beauty often arises not from grand events, but from delicate balances of temperature, humidity, angle, and crystal shape. They are moments when nature bends light just enough to reveal something hidden. And in their silence, they speak of structure in chaos, of cold that gives rise to color, and of the fragile complexity that fills the upper sky. To see an ice halo is to catch a glimpse of the laws of physics made visible. Light dancing through hexagonal windows of ice, painting illusions that are entirely real. These are not merely tricks of the eye, they are frozen whispers of the heavens. Among all the strange and elusive phenomena that dance through Earth's atmosphere, few are as haunting, as debated, and as surreal as ball lightning. Picture a glowing sphere, the size of a grapefruit, drifting silently through the air during a thunderstorm, floating over a field, gliding down a chimney, or even entering a room. It hovers for a few seconds, then vanishes in silence, or explodes with a snap. Reports of ball lightning date back centuries, yet to this day, no one fully understands what it is or how it forms. It is one of the rarest and most mysterious weather events ever observed. Eyewitnesses describe ball lightning as luminous orbs that range in color from orange and red to white or blue. They can appear suddenly, often during or just after a thunderclap, and they seem to defy the usual laws of nature. Some float through solid objects without damage, others follow metal wires or water pipes, and a few have been seen to pass through airplane windows or hover indoors. Many vanish quietly, while others end in small explosions or with a sulfur-like smell. These bizarre details have fueled speculation for centuries, placing ball lightning in the strange intersection between atmospheric science and folklore. Despite thousands of accounts, ball lightning has proven nearly impossible to capture on film or reproduce in a laboratory. It is not a lightning bolt in the traditional sense. It does not strike with thunderous force or flash in a split second. Instead, it lingers, moving slowly, almost deliberately. Some theories suggest it forms from vaporized silicon particles created when a bolt strikes the ground. Others propose microwave radiation trapped in a bubble of ionized air. There are models based on plasma, combustion, even quantum vortices. Yet none fully explain the range of behaviors observed. Ball lightning remains, for now, a puzzle with too many pieces missing. In 2012, scientists in China recorded what is considered one of the first credible video captures of ball lightning. Using spectrographic equipment during a storm, they detected a glowing orb about 5 meters above the ground. It drifted slowly and faded after just over a second. The data suggested a high-energy plasma with trace elements consistent with vaporized soil. Still, the event raised as many questions as it answered. Why is ball lightning so rare? Why does it sometimes appear indoors? Why does it seem to act with intention? These are questions that science continues to chase, in search of a phenomenon that seems to flicker just out of reach. Ball lightning is more than an atmospheric oddity. It represents the limits of human understanding, the edge where observation and explanation no longer align. It reminds us that not everything in the natural world is neatly categorized or fully tamed. For now, it remains a legend grounded in reality, a fiery phantom that appears when the sky is at its most violent. Perhaps one day, with better instruments and deeper insight, we will understand the true nature of these floating flames. Until then, ball lightning remains a symbol of atmospheric mystery, strange, silent, and utterly unforgettable. From the churning storms of the Troposphere to the fading whispers of the Exosphere, we have journeyed through the many layers of Earth's atmosphere, each one a world of its own. We have seen clouds that glow after sunset, winds that circle the poles like sentinels, and invisible fields that push particles into space. We have witnessed beauty formed in ice, chaos sculpted in vapor, and silence illuminated by electricity. And through it all, one truth remains. The atmosphere is not just air, it is the breath, the skin, and the memory of a living planet. It shields us from cosmic violence, shapes the colors of our sky, and responds to even the smallest changes we make on the ground. In its clouds, we see patterns that echo our climate. In its winds, we hear the warning of a warming world. And in its rarest phenomena, like ball lightning, halos, and noctilucent clouds, we find reminders that Earth still holds secrets. The atmosphere does not forget. It stores the stories of our oceans, our forests, our cities. Every molecule of vapor, every gust of wind, every frozen crystal above our heads is part of a grand, ancient system, fragile, powerful, and constantly in motion. As we face the future, we must look upward not only with wonder, but with responsibility. For in the sky above us lies not only mystery and light, but also warning and consequence. The atmosphere is our shield, but it is also our mirror. What we see in it reflects who we are and what we choose to become. Let us listen, let us learn, and let us protect the air that protects us. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.